Okay. Okay. So I had already shared this problem set with you guys yesterday. So all these problems are based on counting, basic counting, right? So let's get started. So the first problem, this is from the assignment 2. So the problem says how many permutations a1, a2 up to a3m of the set of the first 3m natural numbers are there, such that for every index the difference k minus ak is divisible by 3. So what does this mean? That we have to count the number of permutations of this set such that for every index the difference of the index and the number that is present at the index, that difference is divisible by 3. Okay, so how do we solve this? So first of all, note that when will 3 divide this difference? So when will 3 divide k minus ak? So this is going to happen only when the remainders obtained on dividing k and ak by 3 are equal, right? So what we have is that right, this is the equivalent condition of saying that 3 divides k minus ak. Okay, so now what are the possible remainders when some number is divided by 3? It's 0, 1 or 2. There are 3 possible remainders. So let's consider the first index, that is a1. So what do we want? We want that 3 divides 1 minus a1, right? And when can this happen? When the remainder, so this can only happen when a1 is of the form some 3l plus 1 for some integer l, right? That is a1 must leave remainder 1 when divided by 3. Similarly, consider any index which leaves remainder 1 on division by 3. For example, consider the indices 1, then 4, 7, 10 and so on. So all these indices, for all these values of k, the remainder when this is divided by 3 is 1. So for all these indices, the corresponding values, that is a1, a4, a7, a10, all of these should also leave remainder 1 when divided by 3, right? So okay, similarly, if we consider the indices 2, 5, 8, 11 and so on, that is the indices which leave remainder 2, so the corresponding numbers should also leave remainder 2 on division by 5. So then what is happening? So if you consider any of these indices 1, 4, 7, 10, how many such indices are there? So this is up to 3m minus 2, right? So there are m minus 1 indices, right? And in these indices, in these positions, the corresponding numbers should also leave remainder 1 when divided by 3. And how many such numbers are there? There are again just m minus 1 numbers. So out of the numbers 1, 2, 3 up to 3m, there are m minus 1 numbers which leave remainder 1 on division by 3. And similarly, so
wait, isn't it m?
so if you consider which in the set 1, 2, 3 up to 3m, which numbers leave remainder 1 on division by 3? Exactly these, right? 1, 4, 7 up to 3m minus 2, and there are m minus 1 such numbers. So if you count this set, so the 1 is basically 3 into 1 plus 1, then this is 3 into 0 plus 1, Oh, okay, sorry. Oh, yes, yes, it is m. Sorry, yeah, you were right. So there are m indices, and corresponding there are m numbers. Okay. Okay, so in these particular indices there are m numbers, and we can rearrange them, right? So in these corresponding indices 1, 4, 7 up to 3m minus 2, there are m indices. So these corresponding numbers can be rearranged in any order among these indices. So then, so these numbers, so since there are m numbers and there are m indices, so the number of ways is m factorial. Similarly, in exactly the same way, if we consider the indices 2, 5, so similarly, right, and the corresponding number of ways is again m factorial. And similarly for the other case, similarly for the indices 3, 6, so again this is m factorial. So hence total number of permutations is going to be m factorial cube, right? Okay, so yeah, is this clear? So yeah, so basically it's like rearranging the numbers in the appropriate indices. Okay, so if this is clear, we can move on to the next question. Okay, so this question says that suppose we are given two positive integers p and q, where p is at least q, then show that the number of northeast lattice paths from the origin to p comma q that do not go above the line y equal to x is this quantity. So what is this saying? So if you draw the Cartesian coordinates, so here there is 0 comma 0, there is this line y equal to x, and since p is greater than equal to q, so the point p comma q is somewhere here. So what do we mean by northeast lattice paths? It means that we are only allowed to move either to the right or up, right? So basically from the origin to the point p comma q, we have to reach through a sequence of right and up moves. Okay, so for example, one possible sequence of move might be first you move right, again right, up, right, this, and so on. So somehow you have to reach the point p comma q, and the condition is that you should not cross the line y equal to x. So this line y equal to x is here, and you should not cross this. So the question is, in what is the total number of ways by which you can reach p comma q from the origin subject to this constraint? Okay, so now what is the total number of steps that you need to take? First of all, let us count that. So from the origin, in order to go to p comma q, we have to take p many right steps and q many up steps, right? So Okay, so so that means you need exactly p plus q steps. So you need p plus q steps, out of which p of them should be up steps. Sorry, this is right. P of them should be right steps and q of them should be up steps. Okay, so now suppose if you didn't have the constraint that your path should lie below the line y equal to x, then what is the total number of ways? So it's nothing but, right, so you have to take p plus q steps, out of which p of them should be right and q of them should be up. So the number of ways of doing this is exactly this, if you did not have the constraint that your path should lie below y equal to x. Okay, but now from this is the total number of paths. Now from this you have to exclude the paths which cross the line y equal to x. Okay, so now somehow you have to count how many such northeast lattice paths cross the line y equal to x. So in order to do this, we are going to count it in a different way. We will show a bijection between these, let's call these as bad paths. So we are going to show a bijection between these bad paths and some set which we can count efficiently. Okay, so let's call okay, so our task is to count the number of bad paths. Okay, so the way I like to do it is, think of it in this way. So consider any bad path. So a bad path must cross the line y equal to x. So consider the first position wherein it crosses the line y equal to x. So it must be something like this. It may be in the first, it is possible that the first movement itself is the bad movement. That is possible. So let's consider the first time when the path crosses the line y equal to x. So what we do is consider this line. So this line also has slope equal to 1. It's basically a shifted version of y equal to x, right? So now whenever consider any such bad path, so whenever the path crosses the line y equal to x, what we do is we reflect the portion of the path. So the path looked something like this, maybe here, and so on. So what do? We reflect this portion of the path with respect to this green line. So what will the reflected path look like? Something like this, right? You understand? So this red is basically the reflected version of the blue part. Okay, so since this point is 0, 0, this particular point, that is the reflection with respect to this green line, this is nothing but -1, 1. Okay, I hope this is clear. So this reflected point is -1, 1, and every right move here is an up move here, and every up move here is a right move here. Okay, so by this reflection, so what do? Okay, so we have reflected this portion, and as a result, right and up moves swap each other. So a right move now becomes an up move, and an up move now becomes a right move. Okay, and after this, so after this point, whatever path we had taken, we continue with that. So maybe we had done something like this and reached it, that we do not care. So basically what I mean to say is any bad path corresponds to a northeast lattice path from -1, 1 to the point P, Q. This is the main observation. So there is a bijection okay. I hope this is clear. So this is the main observation, that if you consider any bad path, that is basically a northeast lattice path from the point -1, 1 to the point P, Q. Okay, so we have a bijection between this, and now it is very easy to count the number of such lattice paths, northeast lattice paths from -1, 1 to P, Q. Okay, so and this again is easy. So in order to go from -1, 1 to P, Q, what is the number of right steps we need to take? It should be P plus 1. And what is the number of up steps? This is Q minus 1. Right? So right, the total number of steps is P plus Q. Out of them, P plus 1 are right steps. So the total number of bad paths is this. So hence our required answer okay. Okay, so instead of P plus 1 we can also write Q minus 1 here. It's the same thing. Okay, and this, if you simplify, then this will exactly come out as we want. This P minus Q plus 1 by P plus 1. Okay, so if you just expand this thing, then this will come out. Okay, so this is an important technique, that you find a bijection. So in order to count the number of bad paths, you find a bijection from the set of bad paths to a set which can be counted easily, and here the bijection is obtained by using reflection. Okay, so hence the number of valid paths is this thing. Okay. Okay, so if this is clear, then we can move on to the next question. Okay, so this question says that you have to prove some identity, you have to prove this identity, but without using any math. You have to use combinatorial reasoning to prove this identity, which means, so whenever you are asked to prove something combinatorially, which means you have to count something in two different ways, and then those two values must be equal. So you have to consider, you have to come up with some setup which involves counting, and you need to count it in two different ways, and hence those values must be equal. So here, if you want to show that this thing is equal to this thing, you must come up with some situation wherein you have your aim is to count some value, count the number of such number of favorable events, and you count it in two ways and show that these two things are equal. Okay. Okay, so how do we approach this? So let's look at the form. So what is the LHS saying? LHS is it's n choose k minus n minus 3 choose k. So what does it mean? So which means your setup is, suppose you have n items numbered 1, 2, 3 up to n. What is n choose k? And from these n items you are trying to pick k of them. That is n choose k. And what is n minus 3 choose k? It is when you are having n minus 3 items and you are trying to pick k of them. That is n minus 3 choose k. So then if you take the difference, what does it correspond to? Okay, so let's think of it in this way. So suppose we have a set S consisting of n numbers. Now suppose we want to count okay, suppose we are trying to count this. So we have this set 1, 2, 3 up to n. We want to pick k numbers, but with the restriction that among the first three numbers, that is 1, 2 and 3, at least one number must be chosen. So let us count the number of ways of doing this. So on the one hand, so if you consider the LHS, so the total number of ways of picking k items out of these n items is n choose k. And now how if we consider how many such ways are there in which no number from this set is chosen, that is exactly, which means all of the k numbers must belong to the set 4, 4, 5, 6 up to n, and that is n minus 3 choose k, right? So on one hand, so there are two, we'll count this in two ways. Okay, so in n choose k ways we can pick k numbers, and out of them n minus 3 choose k, in n minus 3 choose k of them, none of these numbers 1, 2, 3 is picked. So in the remaining n choose k minus n minus 3 choose k such pickings, at least one of the numbers 1, 2, 3 is present. Okay, so this is one way of counting. Now let us count it in another way. So let's look at the RHS. So what is this saying? N minus 1 choose k minus 1 plus n minus 2 choose k minus 1 plus n minus 3 choose k minus 1. Okay, so what is the first term? The first term is you want to pick k minus 1 items out of n minus 1 items. So let's consider, so what is our goal? Our goal is to pick at least one of the numbers 1, 2 and 3. So let's count the number of ways in which 1 is chosen, and we do not care about 2 and 3. Okay, so if we fix 1, that is 1 is already chosen, then from the remaining n minus 1 numbers you have to choose just k minus 1 numbers. Okay, so Okay, so in n minus 1, choose k minus 1 such pickings, 1 is already present. So now we have to consider those cases where 1 is not present. Okay, so if 1 is not present, then at least one of 2 or 3 must be present. Okay, so let's consider the number of ways in which 2 is present. So if 2 is present and 1 is not present, so we are left with n minus 2 numbers. And among those n minus 2 numbers, we have to pick k minus 1 of them. Okay. Okay, so then what are we left with? We need to only consider the case where both 1 and 2 are not present. We have already counted the cases where 1 is present and when 1 is absent and 2 is present. So the only case we are left to consider is when both 1 and 2 are absent and 3 is present. Okay, so then so now you are left with n minus 3 numbers, that is 4, 5, 6 up to n. Because you are not picking 1 and 2, you have already picked 3. So among 4, 5, 6 up to n, there are n minus 3 numbers and out of them you are picking k minus 1. Okay, so hence the total number of ways is the sum of these 3 terms. And so we are done. We counted the same quantity in 2 ways and therefore these 2 things must be equal. Okay. Okay, so okay. Okay, so if this is clear, let's move on to the next question. So we have to prove this identity, that for all integers n greater than 1, this identity n choose 1 minus 2 times n choose 2 plus 3 times n choose 3 and so on, this sum is equal to 0. Okay, so for this you need to recall this well-known identity. This thing. So let us try to prove this. So r times n choose r is equal to n times n minus 1 choose r minus 1. Okay, so why is this true? So what is r times n choose r? This. Okay, so you can stop me at any time. I'll try to go a bit slow, but feel free to stop me at any time. Okay, so what is r times n choose r? This is this thing. So that is nothing but this thing, right? So what did I do? Just I split n factorial into n times n minus 1 factorial, and this r divided by r factorial is nothing but r minus 1 factorial. Okay, so this I hope is clear. So now what is this quantity? This quantity is nothing but n minus 1 choose r minus 1, right? Okay, so hence this identity holds. R times n choose R is equal to n times n minus 1 choose R minus 1. Okay, so then if you put this in the identity that we need to prove, what do we get? Okay, this, right? So the first term is nothing but 1 times n choose 1. So that is nothing but n times n minus 1 choose 0. Then the second term is 2 times n choose 2, which is nothing but n times n minus 1 choose 2 minus 1. That is n minus 1 choose 1. Similarly, 3 times n choose 3 is n times n minus 1 choose 3 minus 1, and so on. So like this. So what did we get? N times this thing, right? So it's an alternating sequence wherein the even terms, that is n minus 1 choose 0, n minus 1 choose 2, and so on, these even terms have plus sign, and the odd terms, that is n minus 1 choose 1, then n minus 1 choose 3, and so on, these have negative sign. And this, I hope you know, this is equal to 0. So if you don't know, then okay, we can look at a proof. So we want to show that this thing is equal to 0. That is the alternating sum wherein the even terms have positive coefficient, have coefficient plus 1, and the odd terms have coefficient minus 1. This sum is equal to 0. And why is that the case? Because if you look at the expansion of 1 plus x to the power n, so what is this? It is right. So now in this expansion, if you put x equal to minus 1, then the LHS will become 0, and what will happen to the RHS? Note the odd, so minus 1 to the power odd is minus 1, and minus 1 to the power even is plus 1. So we'll get exactly this. And so on. So hence this sum is equal to 0, and here in the wait, can you combinatorial prove it for even n? Finding order even sized subsets. Okay, so you want a combinatorial proof of this quantity. Okay, so what we are interested in proving is basically this. So we want to prove this identity combinatorially. Okay. So Okay, yeah. For odd n it is fine. For even n, how can you prove it combinatorially? Okay, let me think a bit. Okay, better. I'll try to think of this, and I'll write it in the discussion forum in NPTEL. Okay, I'm not being able to think of it now for even n. So for odd n, it is clear that you're just picking odd subsets and even subsets. So there's a bijection, and so this sum is equal. But for even n, the number of terms is different, so it's difficult to find a bijection. But I'll try to think of it, and I'll post in the chat. I'll post in the discussion forum. Okay. Okay. But this identity you must remember, that the odd sums and the okay, yeah, the odd sums is equal to the even sums. It's a very important identity. Okay, so I hope this is clear. So let's move on to the next question. Okay, so we are asked to show again a combinatorial proof of this identity. So what this is saying, that summation of k squared times n choose k, this is equal to n into n plus 1 times 2 to the power n minus 2. Okay, so you have to prove this again combinatorially. Okay, so now again we have to come up with some situation where we will count something in two different ways. So now what is the RHS saying? It's, so if you look at one single term in the RHS, it is k squared times n choose k. So what is basically happening? So n choose k means out of n items you are selecting k items, and then you are multiplying it by k square. So when you have k items, what exactly is k square? K square is just out of these k items you want to select two items, but repetitions are allowed. Okay, so first you select a subset of size k, and then from this subset of k elements you are choosing two elements which might be the same. So yeah, you are choosing two elements, so that is k square. The first element can be chosen in k ways, the second element can also be chosen in k ways, so that is k square, right? And now when you are taking the sum from k equal to 1 to n, basically you are making that the size of the subset can be anything from 1 to n. Okay, so let's do this then. So suppose we have S is the set of the first S is the set of numbers from 1 to n. So okay, suppose we are interested in finding what is the number of tuples of this form a comma x1 comma x2, where a is a proper subset of S, that is a is non-empty, a non-empty subset of S, and these two elements x1 and x2, these belong to A, these are chosen from A. So if you look at it carefully, this is exactly what is there on the RHS. So let's look at the RHS. So the first way to count this is, first you choose A. So A can be chosen in n choose k ways, where k is something between 1 and n. And once you have chosen k, there are k elements in A. So this x1 and x2 each has k possibilities. So then okay, so we get k square. So hence number of such tuples okay. So you take the sum over all k from 1 to n choose k times k square. So this is one way of counting. Now we have to derive the RHS. Can we count this directly? Okay. So what did we do in the first way? We first chose the subset A and then we chose x1 and x2. So why not do it in the reverse way? That first we choose x1 and x2 and then we choose A. Okay. So now if suppose we want to count it in this way, that first we choose these two elements x1 and x2 and then we choose A. So then what are the requirements? We want that both these once we have fixed this x1 and x2, our set A should be such that A contains both these x1 and x2. Okay. So then so now there are two possibilities. Either x1 and x2 are distinct or x1 and x2 are the same. Okay. So if x1 and x2 are distinct, so then the number of ways of choosing x1 and x2 will be just n into n minus 1, right? Because they are distinct, so x1 can be chosen in n ways and x2 can be chosen in n minus 1 ways. Now once we have chosen these x1 and x2, our set A can be anything, can be a subset of any size which contains both these x1 and x2, right? So once we have fixed x1 and x2, out of the remaining n minus 2 elements, we can choose any subset. So right, so A definitely contains x1 and x2, and other than that it can contain any subset of the remaining n minus 2 elements. So then what is the number of ways of choosing A? It's 2 to the power n minus 2. That is the number of possible subsets of n minus 2 elements. So this is 2 to the power n minus 2. So hence the number of ways in this case, so when x1 and x2 are distinct, so this is equal to n into n minus 1 times 2 to the power n minus 2. Okay, when x1 and x2 are distinct. Now the second case is when they are identical. Okay, so then the number of ways of choosing x1 and x2 is just n, right? You have to select one single number and that is both x1 and x2. So this is just n, right? And now once we have selected x1 and x2, what is our A? A contains this particular value and it can contain, out of the remaining n minus 1 numbers, it can contain any subset of that. So A right, it contains x1 and it can contain any subset of the remaining n minus 1 numbers. So what is the total number of ways? It's 2 to the power n minus 1. The number of subsets of n minus 1 numbers. So in this case, what is the total number of ways? This thing, right? So then the so this is the sum of these two things. One is n into n minus 1 times 2 to the power n minus 2 plus n times 2 to the power n minus 1. So this is going to be exactly what we wanted, n into n plus 1 times 2 to the power n minus 2, and that is what we wanted. Okay. Okay, so just in brief, so we counted the number of tuples of the form a comma x1 comma x2, where a is a proper subset of S and x1 and x2 belongs to A in two ways. So either we choose A first and from A we choose x1 and x2, or we choose x1 and x2 first and from that we build A. That these are the two ways of counting this, and by this we get this identity. Okay. Okay, so let's move on to the next question. So this is about Catalan numbers. So I hope you know about Catalan numbers. I covered this in class. So if you do not know, it's let me just define it for you. So so there are many versions in which many ways you can define Catalan numbers. The one which sir covered in class was this. So suppose you have this n cross n grid, or let's say you have 0, 0. You have the line y equal to x, and you have the point n, n here. So again, suppose you want to go from 0, 0 to n, n without crossing the line y equal to x. So this is just the problem 2 that we considered. There, instead of n, n, it was p, q. So now suppose you want to count the number of ways in which you can go from 0 to 0, 0 to n, n without crossing the line y equal to x. So that is the nth Catalan number. So Cn okay, it's the number of ways of going from 0, 0 to n, n without crossing y equal to x, and the value of the nth Catalan number is this. (1 by n plus 1 times 2n choose n). Okay, and the proof is, there are many ways of proving this. One possible way is to use the reflection principle that we used previously. So the total number of ways of going from 0, 0 to n, n when you do not have this constraint is 2n choose n. And now you can map every bad path, that is a bad path is again a path which crosses the line y equal to x. So you can map this path again to a valid path from -1, 1 to n, n. Okay. So then if you subtract those two terms, you will get what this thing, 1 by n plus 1 times 2n choose n. It's a simple proof. But here what this question asks is to show that Cn satisfies this recurrence. That is, Cn can be written as summation k equal to 1 to n minus 1, the k minus 1th Catalan number times the n minus kth Catalan number. So summation k equal to 1 to n minus 1 c k minus 1 times c n minus k, wherein you define c0 is equal to 1. Okay, So we need to show that the Catalan number satisfies this recurrence. So we will use that, and we have to go by the definition of Catalan number, that is the number of ways in which you can go from 0, 0 to n, n without crossing y equal to x. Okay. So in order to prove this, so consider any such valid path from 0, 0 to n, n. Okay, so what does a path look like? So first you must go right, obviously, otherwise it's not a valid path. Then maybe you again go right, then up, right, up. Okay, so suppose consider the first time when you hit the line y equal to x. So you are allowed to hit the line y equal to x, but are not allowed to cross it. So it is possible you hit it multiple times, maybe here. Yeah, so this is a valid path. Okay, so you may hit the line y equal to x multiple times. So consider the first time when you hit the line y equal to x. It may be that the first time you hit is maybe it's exactly at n, n. That is before n, n you did not hit the line y equal to x. That is possible. But consider the first time when you hit it. So let's say this particular point is k, k. Okay, so k can be any integer between 1 and n. Right? So let okay, so this is the first time when the path hits the line y equal to x. So then what we have done is basically we have split the path into two parts. So one part of the path is between 0, 0 and k, k, and the other part is between k, k and n, n. Okay, so now from k, k to n, n, how many possible such paths are there which do not cross the line y equal to x? So so here there are, so from k, k to n, n, there are n minus k steps, actually n minus k right steps and n minus k up steps. So n minus k right and n minus k up steps. So then what is the total number of possible paths from k, k to n, n? That is exactly the n minus kth Catalan number. So that is Cn minus k. Right? So from k, so once you have reached k, k, the number of ways in which you can reach n, n from there is exactly the n minus kth Catalan number. Now suppose we want to count the number of ways in which you can reach from 0, 0 to k, k. Okay, but note that so why is it not equal to the kth Catalan number? The question is the number of ways from going from 0, 0 to k, k is it equal to the kth Catalan number? No. Why? Because you are considering that k, k is the first time when you hit the line y equal to x. So if you consider the definition of ck, you are allowed to hit the line y equal to x multiple times before reaching k, k in the definition of ck. But now you are trying to count the number of ways of reaching from 0, 0 to k, k without even hitting the line y equal to x. Right? Okay, so let's write this down. So first of all, this is Cn minus k. From k, k to n, n is Cn minus k. Now we have to count Okay, so now you are not even allowed to touch the line y equal to x, and so you have to count what is the number of valid paths. And therefore I think it is clear that the answer is not ck, because when you are defining ck, you are allowed to touch the y equal to x line multiple times. Okay, but now the important thing to observe is that what does this condition mean, that you do not want to hit the line y equal to x. So this is equivalent to saying that you do not want to cross the line this, right? So this is nothing but y is equal to x minus 1. This yellow line is y equal to x minus 1. So if you do not want to hit y equal to x, which means you do not want to cross the line y equal to x minus 1, right? So without hitting y equal to x is same as saying okay, so which means you want to go from 0 comma 0 to k comma k without crossing the line y equal to x minus 1. That means, so the first step is obviously to the right. From when you are starting from the origin, first you must go to the right. You have gone to the point 1 comma 0, and then from here you have to go to the point k comma k minus 1, right, without crossing this particular line. So you want to go from the point 1 comma 0 to the point k comma k minus 1 without crossing the line y equal to x minus 1. And now you can notice that this is exactly the setting of Catalan numbers, just you have shifted the line y equal to x to y equal to x minus 1. It's just a shifted version, right? So here you basically have to take k minus 1 many right steps and again k minus 1 many up steps. Okay, so hence the number of ways of doing this is ck minus 1, not ck. Okay, so this is the important bijection to observe, that if you do not want to hit y equal to x, that is same as saying that you do not want to cross y equal to x minus 1. So then it's exactly the number of ways in which you can take k minus 1 right steps and k minus 1 up steps without crossing this line of slope 1, and that the number of ways of doing that is exactly the k minus 1th Catalan number. Okay, so ck minus 1. Okay, so then what is the so then what is the total number of ways? It's right. So the number of such valid paths when k comma k is the first time we hit the line y equal to x is exactly this quantity. So in ck minus 1 ways you go from 0 comma 0 to k comma k, and then from k comma k to n comma n there are c n minus k possible ways, and now k can take any value from 1 to n. So hence cn, that is the number of valid paths from 0 comma 0 to n comma n, you take it's exactly this thing where k varies from 1 to n. Okay, so this is the recurrence for the nth Catalan number, right? So then suppose in some problem you are given some problem and you suppose you find the recursive solution to the problem. That is, so let's say the number of ways of solving the problem is, let's say the number of ways of counting is say f of n, and by some means you are able to get to this recurrence. That is, you are showing that f of n satisfies this recurrence. Then directly you can say that f of n must be equal to the nth Catalan number. And that is what we are going to see in the next question. That suppose we are able to consider some problem, and let's say the number of ways of counting that is f of n, and you write a recursive form of f of n, just the way we did this. So here we arrive at this recursion by locating where it touches the line y equal to x for the first time. Similarly, for some other problem, you can choose some other parameter, and suppose somehow you arrive at this same recurrence, then directly you can say that the solution is exactly the nth Catalan number. Okay, so let's look at this question. What is this saying? That suppose we choose 2n equally spaced points on a circle. Now show that the number of ways to join these points in pairs so that the resulting n segments do not intersect is equal to the nth Catalan number. Okay, so what is this saying? So for example, let's say n is equal to let's say n equal to 3. That is, there are 6 points on the circle. Okay, so suppose you have 6 points on the circle. Now you have to join these points in pairs. So there will be 3 segments which joins these 6 points in pairs, and you have to do it in such a way that these 3 lines do not intersect. So maybe one possible way of doing could be you join 1 and 2, you join 5 and 6, you join 3 or 4. This is one possible way. Another possible way may be you join 1 and 4, then you join 6 and 5 and 2 and 3. Okay, so this blue, the blue lines is one possible solution, the green lines is one possible solution. So what is not a solution? So suppose you join 1 and 3, and suppose you join 4 and 5, but then you are not allowed to join 6 and 2 because this will create an intersection point. Okay, so this is not allowed. So you have to pair up these two endpoints in such a way that those corresponding end segments do not intersect. Okay, I hope the problem is clear. So here in general you have two endpoints on the circumference of the circle. So again, so let's say f of n be the possible number of ways. The number of ways of drawing end segments subject to this. Let's call it f of n. So now in any valid solution, consider to which point 1 is matched. So what is the pair for 1? Okay, so now the thing to observe is that can 1 be matched to any odd number? So let's say suppose 1 is matched to number 3. Okay, then in that case 2 cannot be matched to anyone, because if you want to match 2 to any other number, it must cross this particular line, right? So 1 cannot be matched to 3. Similarly, suppose 1 is matched to 5. So 5 is here. If you match 1 to 5, so there are odd number of points here. So then even if you match, let's say 2 to 3, there will still remain one point which will remain unmatched here, and that you cannot match to any point here, because then it must intersect the line joining 1 and 5. Okay, so like this you can argue for any number. So what this is telling us is that 1 has to be mapped to some even number. right? 1 cannot be mapped to an odd number, then it's not possible to draw n segments, so there will always be something that intersects. Okay, so this is the first important observation. So so 1 has to be matched to some even number. So let's call it 2k. So suppose 1 is matched to the point 2k, where k can be anything from 1 to n. Okay, so let's consider this situation. So here we consider, suppose 2k is here and 1 is matched to 2k, right? So now how many points are there? So this region contains the points 2, 3, 4 up to 2k minus 1. So how many points are there? There are exactly 2k minus 2 points here, right? And how many points are here? There are exactly 2n minus 2k points here, right? So now, since we have joined 1 and 2k, no point here can be matched to some point here. So let formally, if we write it, so let A be the set of points 2, 3 up to 2k minus 1. Okay, so these are the two sets of points. This is A and this is B. So now, since 1 is matched to 2k, so it follows that no point in A can be matched to any point in B, because then it must cross the line joining 1 and 2k. So right, so which means the points in A must be paired among themselves, the points in B must be paired among themselves, right? So then, since this set A contains 2k minus 2 points, so what is the number of ways of pairing them? This will nothing be f of k minus 1, right? Because this is 2k minus 2 is 2 times k minus 1. So the number of ways of pairing them will be f of k minus 1 by definition. Since when there are 2n points, the number of ways is f of n. So when there are 2k minus 2 points, the number of ways is f of k minus 1. Similarly, in set B there are 2n minus 2k points. So the number of ways of matching them will be f of n minus k. That is the way we have defined the function f, right? So okay, so this is f of k minus 1 times f of n minus k is the number of possible pairings when we have matched 1 with 2k. And now, as we saw, k can be any integer between 1 and n. So hence the total number of pairings, which is f of n, is equal to okay, k can be anything between 1 and n. And now note that this is exactly the recurrence for Catalan numbers in the previous question. Right. So directly, since we have already solved this recurrence, so we can directly say that fn is the nth Catalan number, that is 1 by n plus 1 times 2n choose n. Okay. Yeah. So these are seemingly two different problems. So we started, so what definition of Catalan number did we start with? It is the number of ways in which you can travel from 0, 0 to n, without crossing y equal to x. And in this problem we are considering in how many ways can you pair these two n numbers such that no two segments intersect. These are two seemingly distinct problems, but surprisingly both of them, the number of possible ways is the nth Catalan number. So this Catalan number pops up in many other such places also, surprisingly. So yeah, okay, so I don't have any more questions today. So if anyone has any question, then you can ask me, otherwise we can stop today. Okay, so if you don't have any questions, then we can stop, and I'll try to think about the question that.
Hello.
Yes.
Sir,
Yes.
in the strong form of pigeonhole principle,
Yes.
if we have like if it is said that if we have q1, q2 up to qn number of integers,
Yes.
and then if you want to distribute q1 plus q2 plus so on qn
Yes.
minus n plus 1 number
Yes.
of things into n number of boxes,
Yes. Yes.
uh,
Either the
is-
first box contains at least q1.
yeah,
Yeah.
yes sir.
So-
So why do we take q1 plus q2 plus so on qn plus sorry minus n plus 1? Why don't we just consider the sum of the numbers?
Okay, then the proof will not work through. So if you look at, so suppose you have okay, so suppose you have q1 plus q2 plus up to qn. Suppose you have this many number of pigeons and you have n holes. Okay, so what do you want to claim? That wait,
That the first box will contain at least
at
q1
least
number of
okay, at least q1 or at least q1 plus 1, I think. No, or so that depends on what you want. So you want that either the first box contains at least q1 plus 1 pigeons, or the second box contains at least q2 plus 1, or this is what you want, I think, because wait,
I think you're right.
sorry.
I think what you said is right. If you have just the summation qi, then it will be q1 plus 1 or q2 plus 1 and so on.
Yes. So if
No, but that is there's a plus 1 in the summation, sorry.
so I think this is actually there, and yeah, I think the version which sir covered in class, it was like so you have this many number of pigeons, q1 plus q2 up to qn minus n plus 1, and you have n holes. So what sir said was either the first box will contain at least q1 pigeons, or the second box will contain at least q2 pigeons, and so on. At least one of these thing will hold, and that is because if none of these hold, then the total number of pigeons will be at most q1 minus 1 plus q2 minus 2, and so on. Sorry, q2 minus 1 to qn minus 1, which is like q1 plus q2 minus n, but you have one more pigeon. Yeah, so that depends on what version you want. So if you want that some hole to contain at least q1 pigeons, then you must have this many number of pigeons, at least this minus n plus 1 is needed. But if you want like some hole to contain at least q1 plus 1 pigeons, then this number of pigeons suffices, q1 plus q2 plus up to qn. Like you will need at least this many number of pigeons.
okay, so it only depends on how many number of objects that we have
Yes, yes.
we want to have in the box.
Yes, yeah.
Okay.
So Yeah, because so in this case, in this case, what you wanted is you wanted some hole to contain at least qi pgn. That some hole I contains qi pgns. In that case, so you look at the contrapositive of this. You look at you look at the negation of this. So that is none of these boxes contain at least qi pgns. So which means the first box contains at most q1 minus 1 pgns, second box contains at most q2 minus 1, and so on. And so the number of pgns will be at most this q1 plus q2 then minus n, but you have one more pgn here. So that's the thing.
Yes, sir. Understood. Thank you, sir.
Yeah. Okay. So somebody asked about the recordings. So recordings, I think for the last week I shared. If you look at the discussion forum, it is there, and today's one I'll share. Like these notes and the recording I'll share in the discussion forum. Okay. You couldn't find it, but so others, did you check? Rishi and Pranjal? Because
I haven't checked the forums. I haven't checked the discussion.
okay. Okay, fine. I'll then send for both the weeks because I had sent it. So maybe I'll resend that, and I'll also share this. And I'll also think on the this when n is equal to even, how can you show that identity combinatorially, n choose 0 plus n choose 2 and those things, and I'll post in the discussion forum. Okay. 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 So if you don't have any questions, yeah.
Sir.
Yes. Yes.
What is this? Where can we find this discussion forum? Sorry, will
Oh,
will it
so-
be sent?
So you have access to the NPTEL course web page.
Yes, sir. Oh.
Yeah. So there is one tab called Ask a Question.
Okay.
So there
yes.
are many tabs like announcements. Then
Mm.
there are many tabs. So if you go to the tab Ask a Question, there all these things are there.
Okay, fine.
Yeah.
Yes, sir.
And so you can subscribe to it. Like if you can, it's basically a Google group. So if you join the Google group, you will receive those emails in your Gmail also. So
Okay,
Yeah.
sir. Mm.
okay. Okay. So then we can stop today. Thank you.
Debjyoti,
Yes.
are you working with Professor Narayana? How are you in touch?
Sorry.
Are you working with Professor Narayana?
No, I am not. So actually, I am a PMRF fellow. So PMRF is Prime Minister's Research Fellowship. So for that, we have to do some compulsory TA-ship to get the fellowship. So that is why NPTEL is like a platform where we are completing our requirements. So we applied to, I and many of my friends also, we applied to NPTEL, and NPTEL mapped us to the corresponding professors. That way we got.
Oh, okay.
Yeah. Okay. So